In the last video, we finally started talking about the fluxions, or the derivatives. That is, if I start with some equation, some simple equation like y is equal to x squared, what I showed you how to do was go from this equation to the derivative, or the fluxional equation, which is y dot is equal to 2x x dot. And what I'd like to start talking about in this video is show you how to invert this whole process. That is, if I give you some equation which has y dots and x dots, can you tell me what y had to be equal to? And all of this goes under the domain of differential equations. That is, if I initially presented you with the equation y dot is over x dot is equal to 2x, could you tell me what y is equal to? And in this case, it would just be x squared plus some constant, of course. And I'd like to start talking about that topic in this video. And I would also like to start talking about how all this power series stuff, all this power series manipulation is going to allow us to calculate a power series for the natural log of x and the inverse tangent of x. Hopefully you could discern from my previous video that if we had a power function, for example, y equals x to the fourth, the general rule for finding y dot was to take a look at the power and multiply the expression by that power out front. So if we have x to the fourth, we multiply by 4 out front. The 4 becomes a new coefficient. We have x, and we decrease the power by 1 unit, and then multiply by x dot. Or if we wanted to rearrange this, we would say that y dot over x dot is equal to 4x cubed. And we nowadays say that the derivative of x to the fourth is 4x to the third power. Now the question is, can we invert this whole process? Instead of going from x to the fourth to 4x cubed, is there a way to go backwards or to find the antiderivative? And it turns out, of course, there is. And if you have already taken calculus, you probably know this already. But the general rule is, if I have some x to the n power, if I have, let's say, y dot over x dot is equal to x to the n power, to find y, what I do is I add 1, I look at that power there, I add 1, and I write x to the n plus 1, and then what I do is I divide by n plus 1. Just to list out some examples, if I have y dot over x dot is equal to x to the third, the antiderivative is going to be x to the fourth. I add 1 to the 3, which becomes 4, and then I divide by 4. And furthermore, you can see that if I take the derivative of that expression, x to the fourth over 4, the 4 comes out front, multiplying it out front, which cancels the division by 4, and I get x cubed, which tells me that x to the fourth over 4 is indeed the antiderivative of x to the third. And this is the general method for solving some differential equation, x dot over y dot, which has only x's on this right-hand side. For example, if I have y dot over x dot is equal to 2x, let's say to the fifth power, plus x squared, I just apply this rule here to both terms individually. If y dot over x dot is equal to all this stuff, then that tells me that y is equal to 2x to the sixth power. I increase it by 1 unit, and I divide by the new power, which is 6, plus x to the third divided by 3. And to simplify, I get x to the 6 over 3 plus x to the third over 3. And to convince ourselves that y is indeed the solution to this differential equation, we take the derivative of this equation, and we find that y dot over x dot is equal to, let's apply the rule, we get x to the 6 over 3. I bring the 6 out front. 6 divided by 3 is going to be 2, x, and I decrease that power by 1 unit, which becomes 5, plus, if I get x to the third, I bring the 3 out front, plus 3 x cubed. It's going to be x squared, because I'm going to decrease the power by 1. over 3. The 3's cancel, and I get 2x to the 5th plus x squared, which is indeed what's on the right-hand side of this equation. So that tells me that this y, x to the 6th divided by 3 plus x to the 3rd divided by 3 is a solution to this differential equation. And of course, one important thing to note here is that to find the general solution to this differential equation, I need to add some constant here, plus c, for the reason that if I had taken x to the 6th over 3 plus x to the 3rd over 3, and if I just decide to add 2 to that and call that y, you can see that by taking the derivative of this equation, that this is also going to solve this differential equation. You're also going to get 2x to the 5th plus x squared as a solution, for the reason that this constant, the derivative of a constant, is 0. So this is going to be the general method for solving some differential equation or some fluxion equation, which reads y dot over x dot equals some stuff involving only x's on the right-hand side. Hopefully you can see why these power series are so useful. You just need to know that one rule for taking the derivative and the antiderivative for a power function, and you can do just about anything. If I write more generally, if y dot over x dot is equal to, let's say, a0, some constant a0, plus a1 times x, plus a2 times x squared, and so on, where the a's are just the coefficients, I can always say that y is equal to a0x plus a1 x squared over 2 plus a squared x to the 3rd over 3, and so on, just applying that one rule. And then, of course, I should tack on this additional constant of integration here. Well, hopefully you can see that this is very easy. It's always easy to find the antiderivative and a derivative of a power series. But at this point, I'd like to show you how we can use these differential equations and the power series to find some interesting power series of expansions of some very useful functions. Let's have a look at the following differential equation or fluxion equation. Y dot over x dot is equal to 1 over x. And again, if you know calculus, you'll probably know what the answer is immediately. But let's use the power series method. And Newton actually considers a variant of this in the text. He actually considers y dot over x dot is equal to b over x, where b is some constant. Now, we can see here that we can't apply that power rule for the reason that 1 over x is x to the minus 1. Adding 1 to minus 1 gives us 0, and then we can't divide it by 0. So clearly we need another method for finding the solution to this differential equation. And as is very common in the field of differential equations, you can often solve an equation by thinking of a clever substitution. And this is precisely what Newton does here. What he does is, instead of writing x, he says, let's let x be equal to some additional variable, I'm going to call it t, plus 1. He says t plus some arbitrary constant, but again, I'm going to use specifics here. Let's let x be equal to t plus 1. And from this equation, we can see, just by taking the derivative of both sides, that x dot is going to be precisely equal to t dot. So I'm going to make these two substitutions here. On the left-hand side, I have still y dot divided by, instead of x dot, I'm going to have t dot, because x is equal to t dot. And then on the right-hand side, I'm going to have 1 over x is equal to t plus 1. So I'll write that in there, t plus 1. And the whole point of doing this, if we go back to the very first video in this series, I know how to expand out something that looks like this in a power series fashion. And what I'm going to do is do long division on this. I have t plus 1 in the denominator there, and I have 1 in the numerator, and I'm going to perform long division. What I'm going to do is I'm going to ask how many times is 1 going to 1? The answer to that is 1. And then I multiply 1 by the expression here, and I get 1 plus t. I'm going to start writing it in ascending order. and then I subtract. I switch the signs there, get the cancellation, and I get minus t. And then I ask, how many times is 1 going to minus t? The answer to that is minus t. I multiply minus t by t plus 1, and what I get is minus t minus t squared. I subtract, change the signs, get the cancellation there, t squared. How many times is 1 going to t squared? The answer is plus t squared. And hopefully you can start to see the pattern here. When we perform this long division, we're going to get an alternating series, plus minus plus, with ascending powers of t. And if this calculation is foreign to you, check out the first video where I show you how to do all this stuff. So I could say that 1 over t plus 1 is equal to the power series expansion 1 minus t plus t squared minus t cubed plus t to the 4th, and so on. And that's still equal to y dot over t dot. And now I just use that very simple rule for finding the antiderivative of a power series or of power functions. The antiderivative of 1 is going to be t. I take the antiderivative of t, and I get t squared over 2. The next term is going to be t cubed over 3 minus t to the 4th over 4. And hopefully you can see the pattern at this point. T to the 5th over 5, and so on. Still having that alternating series there. And that's equal to y. And of course I can tack on a constant of integration if I want, but I'm going to consider this particular one now. And what I'd like to point out here, if we kind of skip around in the whole logic of calculus, the solution to this differential equation, y dot over t dot, or nowadays we might just write y prime is equal to 1 over 1 plus t, or 1 plus x, or whatever. The solution is the natural log of 1 plus t. So that's what I'm going to write here. I'm going to write that the natural log of 1 plus t is precisely equal to this power series expansion. It's equal to t minus t squared over 2 plus t to the 3rd over 3 minus t to the 4th over 4, and so on. And of course, if I wanted to, I could make that substitution that t plus 1 is equal to x, and I would find that the natural log of just plain old x, just x instead of 1 plus the variable, that the natural log of x is going to be equal to t, but t can also be written as x minus 1. Notice how I'm shifting everything back a unit. It's going to be equal to x minus 1 minus x minus 1 squared over 2 plus x minus 1 to the 3rd over 3 minus x minus 1 to the 4 over 4, and so on. Nowadays, we would call this the Taylor series expansion of the natural log at x equals 1. And if you know calculus, you probably recognize this very quickly. And the last thing I'd like to point out with this calculation is a very interesting infinite series. If I plug in the special value t equals 1 into this series here, to that series, what I get is that the natural log of 1 plus 1, or 2, is equal to, now just substituting t equals 1, I get 1 minus a half plus a third minus a fourth plus a fifth, and hopefully you can see the pattern. That alternating series where the denominator increases by 1 unit each time. This series here, if it converges, which I haven't proven that this actually converges, if it converges to the natural log of 2. And that's a very famous series there, but you can see how easily it's derived from this whole power series stuff. The other differential equation, or fluxion equation I'd like to point out in this video, is the following one. y dot over x dot is equal to 1 over 1 plus x squared. Now, I'd like to do the same procedure, do some long division first. I have 1 plus x squared in the denominator, and then 1 in the numerator. And let me perform this long division here. So how many times does 1 go into 1? The answer is 1. I multiply 1 by 1 plus x squared. I get 1 plus x squared. I do the subtraction, flip those signs, get the cancellation there. I'm left with minus x squared. How many times does 1 go into minus x squared? The answer is minus x squared. I multiply minus x squared by 1 plus x squared, and I get minus x squared minus x to the fourth. Flip those signs, get the cancellation. I'm left with x to the fourth. How many times does 1 go into x to the fourth? It's going to be plus x to the fourth. And hopefully you can see the pattern at this point. We again have an alternating series, and we ascend in powers of 2, in increments of 2. So I'm going to rewrite this fluxional equation, or this differential equation, as y dot over x dot is equal to 1 minus x squared plus x to the fourth minus x to the sixth, and so on. Hopefully you can see that pattern there. And then I use that very simple procedure that we've been talking about, where I take the antiderivative of each term. The antiderivative of 1 is going to be x. The antiderivative of negative x squared is going to be minus x to the third over 3. And then I'll get plus x to the fifth over 5. And again, hopefully you can see the pattern here, just ascending in those increments of 2 and alternating. Now I'm going to get the following power series. And that's continued on. And now, if you know some basic derivatives, you'll know that the derivative d dx of tangent inverse of x is precisely equal to 1 plus x squared, to 1 over 1 plus x squared, which means that the thing I've just found is equal to tangent inverse of x. In fact, this is the power series expansion of tangent inverse. X minus x to the third over 3 plus x to the fifth over 5 minus x to the 7 over 7, and so on. And now, again, I'd like to point out a very special and very famous case of this infinite series. And it comes from the fact that the tangent of pi over 4 is equal to 1, which implies that tangent inverse of 1 is equal to pi over 4. And I'm going to plug in that special case that x is equal to 1, because we know that by plugging in 1, I'm going to get a series which should go to pi over 4. So I've just derived that pi over 4 is equal to, now it's just plugging in x equals 1. That's equal to 1 minus 1 third plus 1 over 5 minus 1 seventh plus a ninth, and so on. Hopefully, again, you can see the pattern that we have this alternating series where we have these fractions where the denominator is increasing by 2 units, that this infinite series here, if it converges, which indeed it does converge, that this converges to pi over 4. Alternatively, I can rearrange that to say that pi is equal to 4 times that infinite series. 1 minus a third plus a fifth minus a seventh plus a ninth, and so on. And this is a very famous series expansion for pi. Although you might not want to calculate pi in this manner, since this series converges very, very slowly. On that topic of series which take a long time to converge, or to really convince you that they're actually going somewhere, I encourage you to look up something called the Shanks transformation. It's a really nice way of taking the partial sums of this infinite series and speeding up the convergence. And what you're doing here is there's this formula that you apply to speed up the convergence. And you'll see that after doing that procedure, taking the Shanks transformation of the series, that this series can be made to converge very quickly to pi. But I encourage you to check this out since few people know about this. I didn't know about it until fairly recently. And I think that'll wrap it up for this video. What I hope I showed you is how if we have some fluxional equation, y dot over x dot is equal to some power series stuff on the right-hand side, how it's very simple to find solutions to that differential equation. And in the next video, I'd like to consider differential equations which have something other than just x on the right-hand side. For example, we're going to consider the equation y dot over x dot is equal to y in the next video. So once again, thanks for joining me for this video. If you enjoyed this video, feel free to subscribe to my channel, like the video, feel free to comment as well, and hopefully join me for the next video.